Part 1 of Unit 13 is the details of acid-base titrations. In case you didn't know, titration is a lab technique used to determine the concentration of an unknown acid or base by using the opposite of a known concentration. So in this picture, we've got a burette containing sodium hydroxide of known concentration, and we're adding it to a beaker of hydrochloric acid of unknown concentration. And through some math, we can figure out the concentration of the hydrochloric acid. Just remember the names of the equipment, and that you're always going to use the opposite. So if we're trying to find the concentration of a base, our burette is going to have an acid of known concentration. A pH meter like the one that was in the picture on the previous page, or color-changing indicators, sometimes both, are used to determine when the solution has reached the equivalence point. And the equivalence point is where the stoichiometric amounts of acid equals that of the base. So when you've reached the equivalence point of a titration, the moles of the known that you added are equal to the moles of the unknown that were already there. So a lot of times people will just say moles of acid is equal to the moles of base. Well, to be just a little bit more specific, the moles of the known base that you've added are equal to the moles of the unknown acid that were already there at the equivalence point. You're going to end up recording the volume of the known that you've added and doing some math from there. The pH meter or the color-changing indicators are used to let you know when you've reached that equivalence point volume. Titrations produce graphs that look like this, called titration curves, and in this one we're adding a strong base into a strong acid of unknown concentration. This first region starts out with a low pH because it's a strong acid, and as we start to reach the equivalence point where the moles of base added equal the moles of acid that were already present, there's a big jump where we go through the equivalence point, and up here we're left with primarily hydroxide ions, giving the solution a basic pH. The equivalence point of an acid-base titration that involves a strong acid and a strong base is going to be at a pH of 7. So when we reached the equivalence point of that strong acid, strong base, let's say we were using hydrochloric acid of unknown concentration and sodium hydroxide of known concentration. Well, this is an acid-base neutralization reaction. We're going to get water and sodium chloride out of it. That's aqueous. At pH 7, the base that we added eliminated all the acid that was there, so all that's present is water and the salt of the neutralization reaction. Now once you've gone past the equivalence point, we saw that the pH kept going up. That's because you keep adding base to it. It's going to raise the pH. But at the equivalence point, the base that you've added has used up exactly all of the acid that was there, leaving you only with the salt and water from the reaction. Now this is a picture of a strong base being titrated into a weak acid, and there's a few noticeable differences. First off, the weak acid has a slightly higher initial pH, slightly different shape through the initial part of the titration. There's still a jump near the equivalence point, but you can see that the pH of the equivalence point is above 7. Whenever we have a strong base being added to a weak acid, the equivalence point is going to be at a slightly basic pH above 7, and the graphs kind of end the same here. The reason why this equivalence point pH is higher than 7 is that as the titration is happening, the conjugate base of the weak acid is being formed, and that conjugate base is also contributing to raising the pH. So it's not just the hydroxides from the strong base that you're adding, but the conjugate base that's forming when the weak acid gets used up also contributes to raising the pH. Now, if we had this reversed and we were doing a weak base, strong acid titration, the equivalence point would be below 7, and that'd be because the conjugate acid is also being formed in the reaction to help lower the pH. So if it's a strong base and a weak acid, equivalence point is above 7. If it's a strong acid and a weak base, the equivalence point is going to be below 7. Now there's a special point on here halfway between the origin and the equivalence point. It's got a fancy name, it's going to fall roughly right in here. It's called the half-equivalence point, and there's some special properties of the half-equivalence point that we're going to look at on the next page. So at the half-equivalence point, that's when you've added half of the volume necessary to reach the equivalence point. There's a special property. At the half-equivalence point, the concentration of the weak acid that we started with has been halfway used up. It's been halfway converted to its conjugate base. That leads us to a special property of the half-equivalence point. The pH at the half-equivalence point is equal to pKa. Remember that pH is negative log of the hydronium ion concentration. Well, pKa is negative log of the weak acid dissociation constant. That's going to be more important later on down the road when we start talking about buffers in 13.3. But to go ahead and illustrate this in the equation form from the graph that we were looking at, we had acetic acid as our weak acid. We're adding sodium hydroxide to it. Well, that's going to produce sodium acetate and water. The half-equivalence point is the part where the concentration of our weak acid and its conjugate base, the acetate ion, if we were treating sodium like a spectator, are equal. The equivalence point that we were talking about earlier, that was where moles of the base added, so the reactant, were equal to the moles of acid already present. So make sure you know the difference between the equivalence point and the values that are equal there, and the half-equivalence point, values that are equal there. And remember that pH at the half-equivalence point is equal to pKa. Okay, so in this picture you can see the changing shape of the titration curve. This is still a weak acid, strong base titration, but as the Ka values get smaller, that means the acids are getting weaker. So the initial pH increases, and so does the pH at the equivalence point. It still takes the same amount to reach the equivalence point, but it's changing the pHs involved in our titration curves. So remember that the lower the Ka value, the weaker the acid is, and that means that the pH values for the start of the titration and the equivalence point are going to be higher. Okay, these graphs are flipped. It's a weak base with a strong acid, so we start off with a basic pH, and as we add a strong acid to it, it decreases until it jumps down through the equivalence point. But it's the same concept as the other titration curves we were looking at. There are several different types of color changing indicators. We need to be able to choose the correct one to use in a titration to make it useful to us. Indicators change over a wide variety of pH ranges. We need to choose an indicator that has a pH range that includes the equivalence point. So in this picture over here, phenolphthalein changes colors between pH of 10 and 8. Well, that doesn't even include the half equivalence point. Or actually, I guess it probably does include the half equivalence point, but it doesn't include the equivalence point that we're looking for. So phenolphthalein would change, but we wouldn't have reached the equivalence point of the titration. The volume at which an indicator changes colors is called an endpoint, but we're most of the time interested in the equivalence point. Over here, methyl red would be a much better indicator. It changes colors between pH of 4.2 and 6. That range includes the equivalence point of this titration. Many times on questions you'll be asked to choose an appropriate indicator for a titration. Well, you're going to want to choose the indicator that changes colors in the range of the equivalence point pH, and sometimes you're given a list of pKa's of the indicators as well. So you're going to want to choose the indicator that has the pKa near the pH of the equivalence point. Polyprotic acids are acids like phosphoric acid, sulfuric acid. that have more than one ionizable hydrogen, they have funny looking titration curves because there's an equivalence point for each hydrogen ion that gets dissociated. So in this picture we're starting with H3PO4, we add some base to it, and then at this point that first hydrogen has been dissociated, so there's an equivalence point there, and we're going to have another one when we've removed the second hydrogen, and then there's going to be an even tinier one up here if we can remove the last hydrogen from HPO3. Your question for this section: which of these titrations would have a higher pH at the equivalence point? Is it A, a known concentration of sodium hydroxide titrated into unknown nitrous acid, or B, known sodium hydroxide concentration titrated into unknown nitric acid?